I guess the motivation not to start it was that there's only so much of this chit chat that you want to.
I think I have to cut it up.
Okay.
Hold on, it should be on.
Oh, cool. Well, doesn't it? Oh, I have to join it. I have to go ahead and do that. Hey, there's somebody out there. There is a person out in cyberspace. Why not?
Do they have an ID?
Jeremy Byron?
Oh, okay. I know that guy.
Oh, you know this one?
Yeah.
Okay. Oh, there we go. Yeah, it's kind of cool.
I guess you can put this on there too.
Yeah, part of the motivation to get so excited was Yetta and Ben Bondo's.
I say.
Sorry?
Part of the reason for getting so excited was.
The non-understanding was this. They had a claim of toxic detection, and if you took completely seriously their central value, it was. I mean, their detection was not that far from the central value of the alignment.
They're much smaller.
Yeah,
but I don't remember that. But then that went away or no?
Well, according to Kendrick, it went away. I don't know if Ben actually considers this or not.
Who were the people that put it out?
It was Ben Bondo and Yellow. I think he's a grad student or something.
Or just in the pocket, right?
Yeah. I think it's the other way around, actually.
Oh, it goes like this?
Yeah.
Is this a good height?
It's definitely reasonable. It's, what they did was intelligent, and it wasn't like any irresponsible. It wasn't like they found something glitchy and just threw it out there irresponsible. It's a very well thought out piece of work on it. But I've been so busy with something else right now, I haven't had a chance to study this methodology in great detail. I think there's issues with how you cut the foregrounds out. And the mask they use for W5 cuts out more of the bulge that was really the one.
Mm-hmm.
So you cut more of the bulge out, less data in your bars.
Sure.
Get bigger, which I think is part of the reason that the 5-year doesn't have. If you take both the central values of it, the 5 years got error bars big enough that it still encompasses zero. And then the other one is the 3-year.
But are there any reasonable models that actually give absolutely no non-Grazianity? Like
no, but the constraint now is like order of 10 to 100. The prediction and the basic minimal plane gain prediction is like 10 to the minus 2.
Okay.
So they definitely produce it, but it's like 4.
Right, yeah.
And then the Planck prospect for Planck or something like order 1.
Order 1.
I think probably 5 or 6 or something like that. Not later than 1. So, that even getting down to the state of the art in the future, you're still 2 orders of magnitude too big. So there's an interest in cooking up something, whether it's contrived or not, that gives something larger, just because it's a logical possibility.
Right. I mean, that sounds sort of similar to the situation for dark matter, where if you were just to throw a dart at a plot of mass versus cross section, it's more likely to land in a region where there is not any signal. But there are models that do give an interesting signal, and those models aren't terribly contrived either.
Yeah. Well, it's like any number of things, right? People spending a long time on the gravity distribution. That's a free. It's a free parameter, and to my mind, I don't see anything more natural than the models that give it detectable and the models that make it not detectable.
Right. Have you heard about this claim, or I don't know if it's really a claim, but this idea by Craig Hogan that
Geo 600 gravitational wave detector may have found, I guess it's quantum noise from the discreteness of space-time. Have you heard this? Yeah, so the Geo 600, it's one of these gravitational wave detectors, like a barometer. It's smaller than LIGO, to transverse displacements. I'm not sure exactly. But they've been apparently struggling for quite a while with some noise force that they couldn't explain away. They're obviously running more experiments to try to determine it. But Craig Hogan wrote a paper just a while ago saying that that's actually exactly the kind of noise you expect just from the fact that we actually live in some kind of holographic universe, then the actual uncertainty in space-time in three-dimensional, or in our four-dimensional space is actually larger than the Planck scale, because the Planck scale is on the boundary, and so that makes sense. It says there's some irreducible noise that is larger than the noise at the Planck level, and so that's the exact same spectrum that people have been struggling with. So he's saying like maybe we, measured the quantum structure of space-time.
I'm gonna have to take a look at that.
Yeah, that was a.
I gotta admit, I'm skeptical at first.
Yeah, no, I think at the moment it's not like a well-developed theory. Yeah.
Yeah, that's an interesting thing. Who did you say it was?
Craig Hogan, he's the director of Fermi Lab.
Oh, right.
He's obviously not a crackpot at
Yeah,
all.
so it's not, if not some guy with a Gmail address and,
No.
and no affiliation or something. Yeah, no, it's interesting, especially when you're doing some research. I somehow understand, by the way.
Yeah, I don't think, I haven't heard talk about everything. It's more like what I saw in some science news press or something like that.
Round people up just in case.
There's a lot of talks here, I imagine. So.
Yeah, well, the last week was because it's job season. We've been having extra talks. Easily forget what the schedule is.
Hey,
How are you?
This is good weather, but
it's cold, but it's beautiful.
yeah, it's good. Well, it's now.
It's been cold also. Yeah, there's been actually for the last week sort of a little bit. It's not as a real snow cover up here, but the patches of ice.
Here, we haven't seen it slow.
Yeah,
for some time. I think it was in the spring.
Right.
It's something.
But somebody was telling me that there's more snow. Hopefully it's really beautiful.
I said the same about last week. Before that, I don't know because I haven't been. Well, how's Princeton? Hanging out?
Yeah, it's good.
Have you, when is under that?
Yes, I think in the fall. I haven't actually done days.
And he's around? Is he over there?
I mean, he's not quiet sometimes, but he's not around regularly. He's good. I think it's only just now starting to first in school.
Different tool.
Starting tomorrow.
People still there? Or yes, so I know he's been trying to negotiate something.
In Australia?
Procedure, I don't know if it's CITA or
Before you came
Department
here?
or something. Because I think
Where?
it was quite one of these. He's a leading figure there, so have with them, you will see with all the I know with him, so now I'm going after him.
Okay. Yeah. Well, you can maybe talk to them.
It's in open office right now, so I can turn it into a PDF and it won't have a movie.
Doesn't matter. I can turn it, well, it'll be in PDF when I get most
Oh,
of
so I'll
it.
send it, I'll just export it as PDF.
I can do it on when I post stuff, so it's. Oh, you mean your address?
Okay, now it's a pleasure to introduce Michael Kahlon. As you see from the name, he's definitely German, and he's now since 10 years in the United States. Originally, he studied physics, as myself. He made his undergraduate at California Institute of Technology in Pasadena, and then made his PhD with the supervision of Madao and Substructure, and since 2006 you are in Princeton. And now we want to talk about Galactic cold dark matter substructure and prospects for indirect or direct detection.
Thank you. All right, thank you for the invitation. I'm going to be talking about results from our Galactic simulation, which this is a picture of, a projection of. This is a numerical simulation of the dark matter structure in a Milky Way scale halo. This work was done in collaboration with Guillermo Madao and Jörg Diemann, who are at UC Santa Cruz, and also Masa Temple, the postdoc, who's now moved to the University of Michigan. And then we recently teamed up with a group of people from Zurich, Ben Moore, Joachim Stadl, and Doug Potter. And some work that I hope to get to at the end of the talk on direct detection. I've been working with Neil Weiner at NYU.
Your collaboration emails are all in German?
Yes, these are Swiss people, actually.
Swiss German.
Actually, only these two are Swiss. Yeah. Okay. So there's probably not much need for an introduction here and evidence for dark matter, but just in case there's some people in the audience that may be working on planets or something like that, I just thought I'd briefly go over this. There's, of course, evidence for dark matter on many scales in the universe. The largest scale is the CMB. We know that the fluctuations of the temperature anisotropies best explained with the power spectrum in a lambda CDM universe. Similarly, on somewhat smaller scales, the distribution of galaxies is shown from the Sloan Digital Sky Survey. It's not uniform, it's got voids and walls, and again, the statistical description matches the CD, a cold dark matter universe. The scale of individual objects, we have, of course, galaxy clusters. Zwicky, back in the beginning of the last, or 1933s or so, proposed the existence of dark matter just because the galaxies in the cluster were moving way too fast and there needed to be some additional matter to hold them together. But also, you can't really see them in this projection, but there's, of course, gravitational lenses, straw marks, and so on that, again, the best mass models that can reproduce the positions of them require a substantial amount of dark matter. The bullet cluster, which I'm sure you've heard about, also provides very nice evidence for separate baryonic and dark matter mass contribution. And then on the scales of individual galaxies, we have spiral galaxies whose rotation curves are flat. And the smallest scales for which we have any observational evidence are dwarf galaxies, which of course are orbiting larger disk galaxies. In the case of the Milky Way, there's 20 or so dwarf galaxies known, and from looking at the velocities of stars and the centers of them, we can infer what the potential is that is governing their motion, and that allows you to infer a mass-to-light ratio, and in many cases the mass-to-light ratios in these objects are tens, hundreds, in some cases even up to 1,000, so they're also very dark matter dominated. So I want to be talking today about dark matter from numerous different directions. First of all, the numerical simulations, I'll get to that in a minute, but now is really a very exciting time to think about dark matter and try to make predictions for what various experiments would see, because there are so many different experiments that are coming together all in the next 5 or 10 years. Of course, there's the LHC, which is going to turn on again later this year, and might produce supersymmetric particles, which of course are a good candidate for WIMP dark matter. I'm not sure how soon we're going to learn anything directly about the mass and cross-section of the dark matter particle, even if it does detect supersymmetric particles, but nevertheless, this would be a very encouraging sign. And then there's two other avenues that I'll be talking about. There's the direct detection experiments, in which you're scattering a WIMP off of the nucleus and hoping to see the recoil energy. And there's really a number of different experiments there with different techniques, scintillation detectors, ionization detectors, phonon detectors, and they're making lots of progress, building bigger and bigger detectors, becoming more sensitive. And then on the last aspect here is the indirect detection, where of course you're trying to observe the byproducts of annihilating dark matters in regions of high dark matter density. And again, there's different approaches there too. You can look for the gamma ray signal, and of course there's the Fermi Space Telescope, which I'll be focusing on a bit in this talk. There's also atmospheric Cherenkov telescopes, which can detect gamma rays from these events. And then there's the sort of complementary point of view, which is the antimatter signal from the dark matter annihilations. And there's been some recent excitement about results that were announced from Kahlon, also from Attic and EDS. There's also a neutrino signal, which I won't be saying much today about. So for the next few slides, I want to focus on the dark matter numerical simulations, which have also made an enormous amount of progress over the last few years. In particular, there's our Via Lattea project, and then also the Aquarius project from the Virgo Consortium over in Europe. So this is Volker Sprengel and Simon White and Julio Navarro and so on. Both of these have now been able to produce sort of on the order of billion particle simulations and are resolving a lot of this dark matter structure that could have potential signatures for these types of experiments. Okay, so I'll jump right into the numerical simulations. This is what the analysis, the work I've been talking about is based on. This is our Via Lattea simulation. Via Lattea is just a Latin or Italian for Milky Way. This is the second one in our series. These are cosmological simulations. Maybe I'll start with one movie that I have, which is just this is just actually the final output of the simulation. So there's no time evolution here, and the camera is just moving around. You've seen kind of movies before, but this is just to highlight all the dark matter structure that we resolve. These simulations are cosmological simulations, so that means the whole box that we simulate is 40 megaparsecs in this case. But they're not at all at a uniform resolution. We have multiple different particle masses, and all the high resolution particles, the lowest particle masses, are stuck in the initial conditions in such a way to resolve the final object that we care about, namely the Milky Way galaxy, at very high resolution. And so here, the main point to take away from this picture, the qualitative point, is that the halo is not at all smooth. There's lots of lumps and essentially all scales that we can resolve in our simulations. Lumps and the bigger lumps themselves have smaller lumps, as you'll see in a minute.
All small lumps look very smooth.
Well, there's some actually just artifacts from projecting them, and it's true that as you get to the smaller and smaller objects, you just have less particles in them, so they end up being smooth, even though the expectation is that they wouldn't really be smooth.
So what's the axis ratio for the density profile?
It's a triaxial ellipsoid, and so it depends a little bit on radius, but it's about 2.
2 to 1.
Yeah, it's actually fairly pro-like. So, of course, this is actually a good point that I should mention that you already know that this is an only dark matter simulation. There's no gas physics in there at all. So the expectation is if you do have gas cooling, it would tend to make the halo a bit more round. At least that's what people see in sort of preliminary baryonic simulations. This all was made possible through some computing grants. The INSIGHT award we got from the Department of Energy. We spent about 1 million CPU hours on this Oak Ridge National Lab Jaguar supercomputer. These simulations are very expensive just because you're going to very highly nonlinear regimes, so it becomes computationally very expensive. We don't just have one simulation. We have a number of them. The first one we did in the series, Galactic 1, had about 200 million particles. They each had a mass of 20,000 solar masses. The one I'm basing my analysis on now is our most recent one, which is 1 billion particles, and every particle has a mass of 4,000 solar masses. Now, our collaborators at Telesc, with whom we've teamed up, they've run this G-halo series, which is an even larger, or even more particle, 2 billion particles in this case, again, a Milky Way scale halo. So when I say it's a Milky Way halo, all I mean is that we picked a halo that has sort of the right mass, the right circular velocity profile, or Vmax, and hasn't undergone a major merger since Redshift 2 or so. So this is not a constrained realization where we actually have, an Andromeda galaxy nearby, or the large and small Magellanic clouds or anything. So in that sense, it's just a statistical comparison. So here's some results that are kind of new to this simulation. Because we have so many more particles than had been achieved in previous simulations, we're starting to resolve more and more of the structure closer to the center of the host halo.
But just in your last slides, you had a little insert, or you paused it called phase-space density.
We'll get to that. Actually, that's the comparison here. So what I'm showing here on the left is a projection of about a 40 kiloparsec sphere in physical space density. So this is just mass per space volume, and so that's what's colored here. So you see a lot of subhalos that stick out. Here's that sort of host halo density, and you can see there's some amount of structure. On the right, though, we plotted phase space density. So this is a projection of phase space density. This is still a 3-space projection, so we're just projecting down a 3-dimensional volume. But the color now doesn't color configuration space density, but phase space density. So it's mass per volume in space, per volume in velocity space. So what that means is that particles that are moving together, that are cold with respect to each other, are going to end up having a higher density than particles that are hot with respect to each other, in addition to particles that are dense in space and configuration space. So what that means is that particles that belong to halos, like these particles, still show up very predominant. They're more extended, of course, because there's more particles here that aren't very physically dense, but still are bound to the structure, and so have a higher phase space density. But interestingly, also there's these additional features, these streams that start popping out. So these are particles that don't show a very high density here. You can't really see any structure here in the physical space density, but they are cold with respect to each other, so they're all streaming in one direction, and so that gives them a high phase space density. And these are presumably just dark matter halos that have been disrupted by tidal forces, and so you can see sort of the tidal streams leading and trailing. And there's a whole bunch of them in this region. And so this is something that hasn't really been seen before in numericals, at least in the central regions of cold dark matter simulations. And it was kind of exciting, but we're still in the process of sort of quantifying this, running, trying to isolate which particles actually belong to the streams and determining how streamy the central halo is. Yes?
Sorry, that's a question. You said that those particles are higher density, but the blue is the lower density.
Right, they're high space density, but of course there would be many particles below here too, which are in this plot just invisible, colored with that. So the various centers are, there's some green dots here, and if you zoom in, there would be some with very, very high space density too. They're just, you can't see them in this projection. Yes?
What's the projection? If you integrate over all phase space, it's just density again. So you've got a moment, or what do you?
No, so what this means is like you could imagine, this is not exactly what we did, but you could imagine splitting up the space into a 6-dimensional grid and then just calculating how many particles are in the volume element in phase space. And that gives you a density in phase space. So every particle has now associated with it a scalar, which is the phase space density. And now we project in 3 space and just color according to phase space density.
So for every particle, you calculate its phase space density.
Yeah.
And then you take the average of the particle phase space densities, which is what you plot over here.
It's not really an average, it's more of just a projection. Which is a projection in space. So every particle has a color, which is its phase-space density, and it has a position in free space, and we've just projected that down in free space.
So it's just positions of it's just particles.
Particle positions.
Except the particles are color coded according to their phase.
So it's the same as that, except that the coloring depends on.
It also takes into account velocity information. It's not just how close they are in space, but also how close they are in velocity space.
It's not color coded with temperature.
What entity, like, basically, like, that's the entity of the particle.
So can I just follow this up?
Yeah.
So exactly what did you do to do the phase-space?
So
how did you represent the distribution function?
So this is an adaptive gridding method. You couldn't really actually just split up the whole volume into a into a uniform resolution grid, where you would not get a very high resolution. But instead, it's split up adaptively in such a way that you're trying to minimize the entropy.
Sure, but is it using a tessellation?
No, it's not a tessellation. So that's what I'm saying. It's an adaptive gridding in 6-dimensional
Oh,
space.
I see.
And that would refer you to.
Rectangle.
So we actually, yeah, it is. It's just not uniform resolution. And actually, this is not a code that we developed ourselves. It's a code called NBID that Sanjeev Sharma wrote at Columbia. It's publicly available. You can download it off SourceForge. It's not yet, or the public version is not parallelized, and so we wouldn't be able to run this code on the entire simulation volume unless we restricted ourselves to the central region.
So if you try to do something like SPH algorithm in the 6-dimensional space, would that actually be effective?
Possibly. So what people often do is just calculate separately a physical space density and separately a velocity dispersion, and then just do rho over sigma cubed.
Yeah.
But that's not really doing the same thing, because you're determining a velocity dispersion in space as opposed to actually determining the structure in velocity space. So you're determining a velocity dispersion based on the nearest neighbor in space, which isn't the same thing. So you do want to do something. I think you do want to do something a little bit more complicated, and you could do a tessellation, like you said, a Voronoi tessellation or something that would also give you.
It's just that this problem, Columbia, when he was at CITA a long time ago, Dimitri, you will remember, he wanted to devote his career to phase-space calculation, but it was hopeless at that time.
Well, he's doing it now.
Yeah, I know. So it's now approaching the point where you can actually do the full distribution function via embodied techniques. But it's still not there. I mean, you're probably going to come up with further resolution problems as you go along, because phase-space is notoriously.
Yeah, this is actually, this is not going to be the focus of the talk. I just wanted to sort of highlight this as one of the results from our simulations. So I'm going to move on to my one slide on the missing satellites problem. This could be the topic of an entire separate talk, but I want to focus my talk today on the direct and indirect detection signals. But since most people always ask me about it, I thought I'd briefly mention it. So the missing satellites problem, of course, is this discrepancy between the number of subhalos resolved in simulations and the number of visible satellites orbiting the Milky Way. So the number of visible satellites that are orbiting the Milky Way has recently grown by a factor of 2 or 3, thanks to really nice work done with the Sloan Digital Sky Survey, which has gone deeper, and people have used sophisticated techniques to pull out very faint objects from the data, and have been discovering more and more of these. So now the total census is up to a bit more than 20 or so. The sky coverage of Sloan is shown here, and the red ones are the ones that were newly discovered in Sloan. So then if you just sort of extrapolate and ask what if we had a Sloan over the whole sky, then maybe we would expect to see 50 or 60 of them. Of course, the question is, like, how do you compare these to the dark matter halos in the simulations? So one way of doing it is just looking at Vmax. Vmax is the peak of the circular velocity curve, and it's some kind of a proxy for mass. And so what's plotted here is a cumulative Vmax curve, the number of halos above a given Vmax versus Vmax, and the blue line is what we get from Via Lactea. You can see it's a nice power law rising towards smaller and smaller Vmaxes. And then the black line is what you get by applying some sort of very simplistic inversion of the central velocity dispersion of the stars measured in the galaxies to get Vmax. And you can see there's quite a discrepancy here. The dashed line is if you allow for a sky incompleteness, so you get boosted a little bit here. But this discrepancy between the blue line and the red line is the missing satellites problem. And it used to be thought that this would be a problem for cold dark matter itself, that you really needed to somehow change the nature of the dark matter particle, maybe make it warm dark matter, in which case the power spectrum would, there wouldn't be any power on small masses, so you could maybe make this agree. I believe that it's not really necessary to invoke such drastic modifications of our sort of standard paradigm. Instead, the solution probably will lie in some kind of astrophysical feedback scheme or something like that. In that case, maybe the epoch of reionization distinguishes halos that are able to form, allow gas to collapse and form stars from those that don't. Another possibility is that there's really just observational completeness above some mass range. That really, if we had much better instruments that could really probe out to the outer edges of the Milky Way halo, we would discover another 100 or 200, and that could make this disagreement go away. So this is still active, ongoing research. In fact, there was a preprint on Astropage today addressing this problem, and arguing that differences in reionization, or the uncertainty in the epoch of reionization, can make a huge difference in how many halos could host stars. So, as I mentioned, as I just said, I want to move on. Okay, go ahead.
So what's the standard typically?
So this is something that we can't very well address because our effort has been focusing on one halo and resolving it with a ton of particles.
So
there is like looking at the literature and looking at other people, is like a factor of 2 or so, maybe close to, roughly a factor of 2 in the abundance of subhalos. So there is some scatter, but it's not, there's not huge differences. Not order of magnitude.
-3, right? The blue line is
Yeah, sorry.
-3.
Yeah, I'll get to that in a minute.
A substantial fraction of the mass actually is bound up in the least massive, the coldest objects.
Yeah, so that's, again, a topic that has been, I don't know, had some controversy. If instead of talking about Emax, you ask about the mass function, have some way of estimating mass, then the slope of the mass function is close to m to the -2, and that is, like you just said, well, that's equal mass per decade, and so therefore there would be a lot of mass in the low mass objects. When we measure it, actually, it's slightly shallower than that, 1.9 or so, so technically it's actually the most massive objects that dominate, but it's sort of, it's right on the cusp. And actually, there's probably no reason to expect the mass function to just be a single power law over many, many orders of magnitude. Probably, just like in pressure theory, it probably relates somewhat to the power spectrum, and maybe it should roll over. Okay, so I have a few more slides on just the population of subhalos that we resolve. So people often are interested also in the central density profile. So here I'm showing the density profile of the host halo in black lines. This is density as a function of radius, and you can see this sort of familiar NFW-like profile with an outer slope that goes r to the -3, and then it rolls over r to the -2. And then in the center is still cuspy as far as we resolve it down. This dashed vertical line here is what we estimate to be our convergence radius for Via Láctea 2, roughly 380 parsecs. And down at our convergence radius, our best fit central slope is 1.2, so it's still cuspy. So we're not claiming that that is the asymptotic slope, but that is the slope that we measure here. Now there's also been a number of studies arguing for something called an inostle profile, in which the density profile rolls over towards smaller and smaller radii, and we get a good fit with an inostle profile too. And in fact, I should mention for the G halo, the host halo that I mentioned earlier, this central slope in the innermost radius that we trust is 0.8. So it's still sort of around the NFW slope, but has become a little bit shallower. So we still think this is not really a fully resolved question. What is actually the central slope? And furthermore, we can only really talk about the central slope down at the radius that we have resolution at. So we don't really want to address the question of what is the asymptotic slope. I'm also showing here the density profile of the 10 most massive subhalos in the simulation. And you can see they have sort of similar profile. When you actually scale them by the scale radius, you can see they fall nicely on top of each other, except in the outer regions where, as you'll see later, tidal mass loss has removed mass from the outside. On the right, I'm showing the abundance of subhalos. This is this Emax to the -3 slope that really just mentioned. So I'm showing the abundance of subhalos, all the subhalos here in the central 100 kiloparsecs and the central 50 kiloparsecs, and they are a nice power law, Emax to the -3. Then again, if you scale the Vmax function by some appropriate value, you can show that the subhalo substructure Vmax function also looks similar. There's a fair bit of scatter, and it's not clear whether they really are self-similar or maybe they actually have somewhat less substructure. There's been some results from the Aquarius simulation that seem to indicate that these actually have significantly less substructure. When we normalize it like this, we find that within scatter, they seem to agree with the host halo. So in that sense, we have a picture that the density profile looks similar to the host halo profile, and the abundance also is somewhat similar. Now here's this, I guess just a shot of this substructure. So these are 4 of the more massive subhalos, and they themselves have lots of subhalos in them. So in that sense, the hierarchical picture is preserved. Now the evolution of these subhalos is governed by tidal mass loss. It's one way of illustrating this is here I fit ellipsoidal shapes to the subhalos as a function of time for the different outputs. So I just picked one subhalo here and plotted its orbit. You see it undergoes a pericenter passage here, and then it moves back out and undergoes another pericenter passage. But the major axis of the ellipsoid always tends to point towards the center, and that's a good indication that it's really tidal forces that are distorting it and keep orienting the ellipsoid towards the center. The center here is indicated by this red symbol. If you look at the orbital evolution of them, you can see that the subhalos undergo a wide variety of orbits. Some undergo just many pericenter passages, or just one, or here's one on first infall. And associated with that is mass loss. So every time they pass by the center, a lot of mass is tidally stripped off. So you can see the mass here initially grows. It's just hierarchical merging, and then starts being stripped off as it enters the host halo and starts orbiting. More consequences of this mass loss. But here on the left is I'm showing the retained mass fraction, comparing the mass, or Vmax, at redshift 1 to the amount of mass that it's able to hold on, retained mass fraction by redshift 0. So you can see that very massive objects lose a very large fraction of their mass, 90% or more. As you then move to lower and lower masses, they are able to hold on to more and more of their mass, and then there's a turnover in this curve. And we believe this is just due to numerical resolution, that these halos just are not resolved well enough to hold on to their mass in the simulation. Okay. One point that's interesting is that of all subhalos that we identified at redshift 1, almost all of them, 97% of them, still have an identifiable remnant at redshift 0. So if you ask about things like the annihilation luminosity, which I'll get to later, it doesn't really matter that they've lost 90% of their mass or so. What really matters is whether or not the core is preserved, whether or not they still have a remnant. And that actually turns out to be the case, that almost all of them, at least from redshift 1, still have this irreparable remnant. The concentration here, this is a different way of defining concentration. It's just the overdensity within the point Vmax. So the numbers here are much larger than maybe you would normally be used to. But you can see that this concentration grows towards the center. So subhalos that you find close to the center of the host halo tend to be more concentrated in this definition. This is just a consequence of tidal stripping, having removed mass from the outside in and lowered the value of our Vmax, thereby increasing the overdensity in the central regions.
Do you expect a different distribution of the gas to change the story? Change quantitative.
So it might change the story in the very central regions, yeah. If you have subhalos that are, interacting with giant molecular clouds, or even with individuals, or stars or star clusters, that could disrupt some of them more. I would say out in like the 20, 30, 40, and farther out region, probably not so much.
But the interior 8 kiloparsecs, which are impressed that you've been able to find these remnants, that would be presumably.
I mean, I think that. I don't want to say it's substantially altered. I think that's the region where you really cannot just trust our results. You would have to rely on baryonic simulations of star formation, or at least put in some kind of stellar disk.
Sort of put it in.
I mean, numerically, I've looked at.
That's the problem.
I mean, I've looked at the orbits of our subhalos to see how many of them pass within that kind of region, and you can get statistics on that. But really, to say like what happens to them, or what happens, more interestingly, what happens to the stellar structure there, whether the disk is puffed up. I mean, I think you have to do more work and actually put in a disk. The point of all these slides was just to say, first of all, yes, tidal evolution determines the fate of the subhalos. They lose a lot of their mass, but the mass is stripped from the outside in. So for what I'm interested in this talk, the central cores are less affected by that. And one more evidence of that is the radial distribution of subhalos. So again, the solid line is just the density profile for the host halo. So the NFW profile here in the central regions. And then I'm plotting these different colorful, these colored lines, subhalo number density profiles according to different selections. So in blue, I've just selected everything above a mass threshold, and you can see that there's quite a big discrepancy. The distribution is very anti-biased. And that's just due to the fact that subhalos lose a lot of the mass in the center, and so they've sunk below this mass threshold, so there aren't any in the center. If you instead apply a cut based on Vmax, which is a selection somewhat closer to the center, so not quite as affected by tidal mass loss, then it already is less anti-biased. And if instead you select by a quantity that was picked before the halo even entered the host halo, so the maximum Vmax it ever reached, that's this cyan line, then you can see that the distribution actually follows the host halo mass distribution down to much smaller radii, 20 or 30 kiloparsec or so. So again, if you ask about the host halo as a function of mass, or selected by mass, then you would find much fewer very massive objects in the center. But if you ask about the dense cores, those actually probably will follow the overall mass distribution more closely. Okay, so now this was all I wanted to say about the properties of the subhalos in our simulation, and now I want to transition to indirect detection, one way that we maybe could observe these subhalos. So the indirect detection signal comes from the annihilation of dark matter particles. Here's just a schematic. You have two dark matter particles that annihilate. They could annihilate directly into light, into gamma rays, or into photons, but they're not charged, they're neutral, so they don't directly couple that way. And instead, I mean, you would have to go to some loop level and extension in order to get any kind of signal there. So instead, you consider the annihilation into other particles like gauge bosons or quarks or something, and then those hydronize, turn and give you pions, either neutral pions or charged pions. And the neutral pions will give you gamma rays, and the charged pions will give you pairs. So I hope to say a little bit about both of these signals. For the next few slides, I'm going to focus on the gamma rays. I should also say that there's, of course, many different types of dark matter models out there. You don't have to be supersymmetric particles or weakly interacting massive particles even. But for the purposes of this analysis, I'm just going to assume that it is a WIMP, a supersymmetric particle. So once you make that assumption, you still haven't pinpointed what the particle is. There's a wide range of masses and cross-sections that are consistent with the abundance of dark matter today. So this is from some calculation by Sergio Francesco, or probably he just used dark SUSY actually, which is this publicly available code to calculate the relative abundance of dark matter in various models. But you can see there's a wide range of masses, and in fact it actually goes out to 500 TeV in scale, and there's a cross-section range also that is covers a few orders of magnitude. And what I want to show you is that models sort of in this window actually result in a signal in gamma rays that could be detected by the Fermi Space Telescope over its lifetime. Okay, so Fermi is what I want to focus on in the next few slides. Fermi is the successor to Egret. So Egret already looked at the sky in gamma rays, but Fermi is an improvement on that, and it's an improvement really in all aspects. It has a better energy range, higher effective area, a bigger field of view, better angular resolution. It's about 9 arc minutes above a huge EV. And so it's kind of exciting. The hope is that it's going to detect, first of all, a whole bunch of new astrophysical sources, or at least shed light on more known astrophysical sources. But there's also the possibility of it detecting, indirectly detecting dark matter. So it's been orbiting for half a year, and it's released its first light images quite a while ago. So this is the picture that Fermi sees of the sky after 95 hours of integration. So you can see the Milky Way, you see some pulsars, these are blazars that happen to be going off. And the nice thing is when you compare it to Egret, this is Egret 6 years, and this is Fermi 95 hours, so they're not even that separate. So there will be quite a bit of improvement after Fermi's lifetime of 5 years. The possible sources, of course, are wherever you have high-density regions, since annihilation is a two-body process. So the galactic center is potentially very promising, then dwarf galaxies, or maybe even a subhalo that doesn't host any stars. So I'll be focusing on those two possibilities. So in order to take my simulation and turn it into some kind of a prediction for what Fermi could see, I'm going to be looking at this sort of master equation, which tells you how many gamma rays you would expect from a given pixel in the sky. So I've chosen an angular resolution consistent with what Telesc gives. And there's an astrophysical component, which is just the line integral of the density squared. It's density squared, like I said, because it's a two-body process. And it's a line integral because I'm looking at a fixed angular size, so that goes as radius squared, but then it's the flux, so that's 1 over radius squared. Then here in blue, there's also, of course, contributions from particle physics, so the cross-section and mass, as I mentioned, and also the spectrum, the energy spectrum you get out in gamma rays. For that, I have to assume something, so I just made a very simple assumption that the dark matter particle annihilates into B bar quarks. It actually turns out that the spectrum here is not very sensitive to that. Unless you annihilate it to taus, then you would get a more harder spectrum. But this is fairly generic spectrum. And then I have to put in some restrictions for the detector, like the effective area as a function of energy and so on. So this is what I get just from the simulation itself. I placed an observer at 8 kiloparsecs from the center, and then I spin the sky up in pixels of 9 arc minutes, and I've just calculated what is the line integral of the density squared in all the different directions. And you can see the galactic center is, of course, very prominent. It's both the highest over density and also fairly nearby, only 8 kiloparsecs. But then there's also a lot of these individual subhalos that stick out. So I should emphasize here, this is not a map of gamma ray intensity or something. This is really just what comes out of the simulation. And this would really have to compete with, lots of known astrophysical backgrounds. And I'll be showing you a few of those in a minute. Yeah.
Do you extrapolate, the density profile?
Yeah, that's actually what this circle is. So we contrast our simulation down to this angular size. And then below that, I actually just put in I try different things, r to the minus 1, r to the minus 1.2 or so. But as for reasons I'll be getting into next is I don't want to really make too many active predictions about the galactic center because there's so many astrophysical sources of gamma rays there that my point of view is that we should be focusing either on the sort of diffuse flux around the galactic center or on individual sources away from the galactic center.
Because the relative importance, of the subhalo relative to the center, so is that dependent upon your extrapolation?
No, it's not. Well, only if you say the very center, as in like the absolute center. If you're talking about sort of the more diffuse area, which is what people from the Aquarius group, for example, has advocated, is that we should be searching for this diffuse signal that's not affected by the resolution of our simulation. And in fact, I haven't redone this yet for a G-halo simulation, but the circle would be smaller. It is true, though, that this is one realization. If I put the observer at 8 kiloparsecs along at a different point, then, of course, everything changes around a bit. And furthermore, if I had a different realization, then, again, it's just a statistical realization. So, the galactic center, yeah, this is why I don't think it's a good idea to look directly at the galactic center, even though that is the area where there's the highest dark matter density. And that's because there's lots of astrophysical sources of gamma rays there. So the Hess atmospheric Cherenkov telescope observed very high energy photons from the galactic center out to 10 to TeV here in this plot. And in fact, at first people thought this could be the signature of dark matter annihilations. But then the fact that this just continued as a power law up to higher and higher energies convinced people that it was probably not dark matter annihilation because you would need really a very, very high cross-section to get enough photons from such a high, such a massive dark matter particle. So most likely this is some kind of astrophysical source, and I'm actually not even sure what exactly it is. But as you can see, there's a galactic center source here. There's also a supernova remnant here. If you subtract both of these sources, a whole lot more structures are popping out on the scale of a degree or so. So I don't think that it would be very difficult to sort of untangle the dark matter annihilation signal from the very center here, given this sort of astrophysical, in this case, noise source. Other backgrounds that you have to contend with are the galactic gamma ray background. So this comes from the interactions of cosmic rays with neutral hydrogen in the galaxy. Here's a model of this. So of course, Ebert has measured this, but at an angular resolution and at an energy that is not as good as what Fermi will see. So in order to estimate the background, I'm making use of a model that was produced by Moskalenko and Strong, this Galprop code, which essentially what it does is propagate cosmic rays with some input spectrum distributed along in the galactic center and sees what their interactions with the surrounding neutral hydrogen in the Milky Way is, and looks at the various gamma rays that you get out of that. So you get inverse, gamma rays just from Kahlon decay like before. You get Bremsstrahlung gamma rays, and you get inverse Compton gamma rays. And this is the kind of map you see. And I'm going to show just a few plots of this with the color scale fixed here, so you can see the relative importance of the backgrounds. There's also an extragalactic background, which of of course, is isotropic, so common structure there. This was measured by Egret. Of course, Fermi probably will resolve some of these sources that Egret could not distinguish, and so this maybe is a somewhat conservative background. This is then the total signal when I add in the two backgrounds I've considered and also the annihilation. And I had to pick a mass model and a cross section, but the first thought is, okay, where's everything? I don't see anything. So here's what it was just looking at the dark matter, and here's what it is when you add everything together. It's disappointing. Now, if you actually look closer there, the subhalos actually do pop out against the background. So it's kind of hard to see in the spot, but I put boxes around them. And so I can actually just go and calculate for every pixel that is covered, every pixel covering a subhalo, I can calculate the signal to noise, assuming that you can just subtract out the background. So then you get this number of source photons divided by the square root of source photons and background photons, and calculate a signal to noise. And then I can look at how many of them actually statistically would be detectable at some threshold of signal to noise of 5. Here's a sort of zoom in of the subhalos in the simulation. On the left, these 4 different subhalos. On the left, I'm again plotting just this line integral of density squared. And the pixels now are pixels with approximately the angular resolution of Fermi. And on the right, you can see the corresponding signal to noise map. So of course, the central pixel is always the dominant one, but there's also pixels surrounding it that are just that will be detected as significant, at a fairly high significance. So the total signal to noise in these cases is, tens or so. And the number of pixels that are detected are not just 1, but they seem to have some angular extent. And so I can quantify this as a function of the particle mass and the cross-section, and just look at how many halos would be detectable. So for the most optimistic cases, 50 GeV or so, there would be maybe a few tens of them detectable, and then of course that number drops off as you go to higher masses. And look, of course, also at the angular size. So here you can see that they typically are resolved with more than 1 pixel. The distribution on the sky seems to be isotropic as far as we can tell. And here's some histograms of the distribution of the halos. So people, of course, are always interested whether or not the most detectable halos are the most massive ones or the nearest ones. So it's not so clear cut from this analysis. It looks like there's subhalos that are detectable at various different masses, out to mean maxes of 20 or so. So those would be the size that would actually be massive enough to host a luminous component. And the distances that I find are sort of around 10 kiloparsecs or so. But I'm not sure that this is a fully converged quantity yet. If I had a much higher resolution simulation, it's possible that we would be resolving more accurately smaller mass halos closer to the observer, and then that might change the distribution a little bit. So that requires further investigation.
So those signal to noises are assuming the 5-year.
Yeah, right. Actually, that's assuming 2 years of exposure. So that corresponds to 10 years of glass. The glass is supposed to have a lifetime of 5 years, but then it doesn't have any dispensables, so maybe it'll go for 10 years. So I used a somewhat optimistic time there.
Can you point it to what galaxies?
Sorry?
Can you point Fermi at a what galaxy? Or is it just an all-sky?
It's an all-sky survey, yeah. So it has a 2.4 star radiant field of view, so it's about a fifth of the sky, and it's just orbiting the Earth and just taking images of the sky all the time. So in 1 year, it covered
You can't point it.
Sorry.
You can't point it.
You can, but it's
You don't do this because you don't gain a lot if you point them to sort of new sources. So I think they point only to gamma ray bursts or something that actually is.
That's my understanding also.
What happens if these subhalos also have astrophysical sources?
Yeah, so that would be. Do I have the slide? No. Okay, so there's a number of ways you can distinguish between that. First of all, I should say that subhalos, at least the visible ones that have the dwarf galaxies, don't have a lot of star formation in them, and so there probably aren't going to be a lot of gamma ray sources in them. But even so, there are ways to distinguish astrophysical gamma ray sources from annihilating dark matter. One would be if you had enough photons that you could get a spectrum, you would expect just a nice simple power law from the. For a lot of astrophysical sources, you would just expect a nice power law, but then the dark matter annihilation would have a break at the mass of the dark matter particle. There's also, the dark matter annihilation signal shouldn't be time independent. There shouldn't be any flares or anything like that. And according to our analysis, it should be extended, and there shouldn't be any or not very strong signals by other wavelengths, there are ways to distinguish. I mean, I agree with you that probably nobody's going to believe it unless there's some sort of independent determination of it.
So people have talked about this possibility that, so if the dark matter were perfectly cold, then I guess the density profile would be forming folds or...
Oh, like caustics, yeah.
Caustics,
yeah.
So how far is that from...
So the expectations there are somewhat uncertain, I would say. So that first of all, in numerical simulations, it's very hard to actually detect, to see the caustics themselves. So I'm not sure that we can say anything about that directly.
I was reminded of it because there was this talk by Simon White about doing that precisely by following the phase-space density.
Right. Yeah, so in fact they showed, their work showed that this sort of a picture that people considered in the 70s of sort of having smooth secondary infall, spherically symmetric with no angular momentum, which gives very nice pronounced caustics at well-defined positions, actually is not applicable when you have a realistic halo in 3 dimensions and with hierarchical structure, growth, and so on. Nevertheless, you still have...
It's not applicable because they're just...
There's additional instabilities that destroy these nice caustics, and I mean, the nice spherically symmetric global caustics. So nevertheless, you still have a collisionless fluid, and so phase-space density, you do get caustics somewhat, but they could be on a much smaller scale. I don't think they would be these global features, and so then I'm not sure how I would turn that into any kind of predictions. So people are definitely considering them still, and they might lead to an overall enhancement of the signal. Okay, so now that was all I wanted to say about the gamma ray signal. Now I wanted to say a few more words about the leptonic signal. So in this case, we're looking at the branch in which the dark matter annihilates, in which we're looking at the charged pions, which give you electrons and positrons.
Can I ask you a question about what you previously said?
Yes.
When you do you were just plotting from your simulations into a rho squared at DL.
Yeah.
You could also put in the sigma v, the appropriate sigma v.
Yeah, that's what I did when I actually then made plots of the detection significance. I had to actually add in a sigma v and a mass of the dark matter particle. So and then I just sort of scanned the allowable parameter space, and that's why this is a function of mass or sigma v.
So sigma v is the local sigma v integrated through.
There's maybe a confusion. The sigma in this case is not the velocity dispersion of the particles; it's the cross section of the annihilation, and it's weighted by the velocity. But it turns out for standard WIMPs, the annihilation cross section goes as 1 over velocity, and so sigma v is independent of the velocity dispersion. So I get to some models in which that is no longer true, but okay, so there's currently a number of observations in the Milky Way halo that seem to not require, but would benefit from a population of very energetic electrons and positrons. So I'm not going to have time to talk about all of them, but one of them is the WMAP haze. Another one is this integral 511 keV signal from the Galactic Center. The two that I wanted to mention briefly are this Pamela measurement of positron excess at greater than 10 GeV. That's shown here on this left plot. By now, I'm sure most of you have seen this plot before. So Pamela is a satellite that's been orbiting the Earth and has been measuring cosmic rays, and it has a way to distinguish electrons from positrons, and so it can actually plot positron fractions. So that's what's plotted here in these as a function of energy. So that's what's plotted here in these red symbols. And the solid line here is the prediction, again from this Galactic model, that is supposed to give you the electron and positron fraction just from the cosmic rays in the Milky Way from astrophysical sources. And so you can see there's a very large discrepancy at high energies. This had been observed before by the heat satellite. Those are the open triangles here. Quite see them. But there the uncertainties were much larger, and now the Pamela result has really put this on a more firm footing. At the same time, this balloon-based experiment, ADIC, and also PPD BETS, has measured a similar excess at even higher energies. These experiments cannot distinguish between electrons and positrons, so they're just looking at the total electron plus positron number as a function of energy. And again, you have this prediction from the standard cosmic ray model, and there's a very pronounced excess at an energy of a few hundred GeV, maybe up to a TeV or so, and then it drops back down to the expectation. So both of these together probably don't require dark matter annihilation as a source, but they are intriguing, and they possibly could be explained by dark matter annihilations. In that case, the dark matter annihilations would have to be very local, because the electrons and positrons at these energies have to diffuse through the magnetic field of the galaxy, and they lose energy. So if they were created at 8 kpc or so, you wouldn't actually observe any of these high energy positrons from those sources. So they have to be very local, within 1 kiloparsec or so. And there's, of course, astrophysical sources that could give you electrons and positrons, especially here in this energy range, which are just from pulsars, for example, if there was a nearby pulsar. It's a little bit harder to explain these very high energy electrons and positrons, I believe. So for now, let's consider the dark matter explanation. People have immediately come up with explanations that were based on dark matter. So here is, again, the signal from Pamela is in this light blue result. And here some people, Lars Bergström and Brinkman and Etzer, just plugged in some standard dark matter particles. Here's one with the 70 GeV mass, and here's one with the 230 GeV mass. And they seem to, more or less follow this model fairly well, can explain the Pamela result fairly well. The only problem is that the cross-section they require are 100 or 1,000 or even 10,000 times higher than what is expected from these dark matter models. So they would result in, they would have, if they actually had this type of annihilation cross-section, they would have annihilated away at freeze out, and you wouldn't have any dark matter left today. So you need some sort of large boost factor. So one way you can get a boost factor is to just consider all the lumpiness.
But that doesn't go to as high energies as for...
Yeah, right. So this is only, so when this paper came out, the attic results haven't really been appreciated. So this is only addressing Pamela. But similarly, you can come up with dark matter models that also fit attic, but generally they all require these large annihilation cross-sections. Right, so one way to get this kind of boost is just to consider the lumpiness of the dark matter halo locally. So since for annihilation what matters is the density squared, you shouldn't just assume that the average of the density squared is the same as the average density squared. So there's some kind of a clumping factor, so an enhancement due to the local clumpiness. So this is something that our simulation, that we can try to address with our simulation. We resolve subhalos at 8 kiloparsecs. We maybe don't resolve the entire substructure population, but we at least see some of them, and we can extrapolate. And it turns out that we are nowhere near the required 10 to the 3 or 10 to the 4. So extrapolating from our results, we get a local boost factor of about 1.4. So it looks like, at least from this way, you're going to have a hard time explaining it. You can, of course, also argue that maybe we just happen to be sitting inside one of these subhalos. If we're close to the center, you can get very, very high boost factors, but that just becomes very unlikely just spatially. If you just pick a random position at 8 kiloparsecs, it's not very likely to lie inside of a subhalo at 8 kiloparsecs. So in Galactic 2, only about 1% of locations at 8 kiloparsecs give you a boost factor greater than 10. So it's much less for higher boost.
Now, if you extract, presumably this boost factor is a function of resolution at some level.
Yeah, so that's why I said extrapolating.
So this is already extrapolating to infinite resolution.
This is extrapolating down to so it makes some assumptions, but it's extrapolating down to the free streaming scale, so that would be about 10 to the minus 6 solar masses. So this is extrapolating many, many orders of magnitude below what we resolve. And then I have to put in some radial dependence, to see how many subhalos you actually expect locally at 8 kiloparsecs, because they tend to be more disrupted there. So I put in, what we measure from the more massive subhalos in our simulation, and then just assume that radial dependence continues down to the smaller masses. So if you depart from that, you can probably get somewhat larger ones. But my contention is that you're not going to get 10 to the 3 to 10 to the 4 lumpiness locally.
Now, naively, if you said it's the wear caustics, the version algorithmically, in which case you would say that you take the size of the system divided by the 10 minus 6 and log that, which is not a huge number, but it could easily be 30 or 100.
Yeah, so what I said has, so that's why I said before, we haven't addressed caustics, so I'm actually at the moment not sure what the numbers turn out to be when you make the most optimistic assumptions for caustics. But this calculation does not address that. There's a general problem, though, that if you boost the cross-section even with caustics or so, and you want to get all these electrons and positrons, then you're also simultaneously going to boost the gamma rays from that. And you would very easily run into existing limits from egret or so. So this is actually partially what has motivated people to consider slightly modified models for the dark matter particle. So there's models that have been proposed recently think Weiner and Weiner have one, and also Nima, Arcani, Ahmed, and collaborators, which Nina Weiner is also one of them, have models in which the dark matter preferentially annihilates into leptons. And the way this is achieved here, they postulated an additional dark force carrier, this an attractive force, this phi particle. And in that case, the dark matter particle doesn't annihilate into gauge bosons or quarks, but it annihilates into this new force carrier particle. And if this force carrier particle has a low enough mass, then it's possible that kinematically pions are not possible to result out of the subsequent decay of this particle. So then you may only get electrons and positrons or muons or something like that out of it, but no pions, which would give you the gamma rays. So this would allow you to get, first of all, enhance the number of electrons and positrons, suppress the number of gamma rays you get out of it. And lastly, also, since you now have an additional attractive force, you get this so-called Sommerfeld enhancement, which is the classical analog of this, just gravitational focusing. If you throw a particle at a planet, then the cross-section that the planet has is not just the size of the planet, but if the particle's moving slowly, it's going to get attracted by the gravity well of the planet, and so the cross-section actually is larger. And the cross-section is larger, the slower the particle is. And so the quantum analog of that is the Sommerfeld enhancement, which you get for this attractive force. So now, for just a Coulomb potential, this enhancement just goes as 1 over the velocity. If you actually put in a more realistic potential, as Arcani, Ahmed, et al. Have done, you have a potential, then the whole story becomes a little bit more complicated. You have sort of 3 regimes, large velocities where there isn't any enhancement. Oh yeah, I need to emphasize this again. At large velocities, there's no enhancement. And that's important because at the time of freeze-out, when the abundance of the dark matter particle was set, the velocities were large. And so this kind of a situation allows you to enhance the cross-section locally, today I mean, and the velocities are sub-relativistic, but it doesn't affect the relative abundance, which was set at the time when the velocities were very close to relativistic. Okay, so there's this regime where there's no enhancement, then there's an intermediate regime where the enhancement goes as 1 over velocity, and then at low velocity there's some interesting effects that were also recently pointed out by Latanzi and Joe Silk, that depending on the mass of the dark matter particle, you can end up in a resonance, essentially a bound state, and that will actually lead to an enhancement that goes as 1 over the velocity squared. So you can see here the enhancement is a function of the dark matter particle mass, and these curves, these colored curves are for different velocities, and you can see at certain masses you get very pronounced peaks. And this is also shown here in sort of a 2-dimensional histogram or contours of the enhancement for different velocities. So you can see there's a more complicated structure that you get out of it. And now the cross-section actually does depend on the velocity of the relative velocity of the dark matter particles. So this is interesting because it can possibly explain the Pamela and Attic results, but it's also interesting for another reason that because it seems to boost the low velocity dispersion particles. And so the subhalos in my simulation, of course, have lower velocity dispersion than the host halo. And so those are possibly preferentially enhanced in the annihilation signal. So if I just look at the velocity dispersion of the host halo overall, you can already see the velocity dispersion is somewhat lower in the center. So possibly the center would be somewhat more enhanced too. But also I remind you of the subhalo abundance. So there's definitely subhalos with Vmaxes of 3. And in fact, if you consider this just as a limit, there could be many, many more subhalos at even smaller velocities that would undergo even more of the Sommerfeld enhancement boost. So this is still work in progress, so I haven't really run this through. But here on the left, I have the case that I showed before without the Sommerfeld enhancement. And here on the right, you can see a lot, this is with the Sommerfeld enhancement for a particular choice of coupling and masses. And you can see that the subhalos start popping out much more clearly. So I have yet to really convert this into how many of these subhalos would be detectable in this kind of a setup. And of course, in this case, you have to rely on gamma rays from some other method. So you won't get any, by design, you don't get any gamma rays from the pion decays. But you can get gamma rays from other processes like internal Bremsstrahlung and so on. So if there's a little bit of time left, then I'd like to just give a brief outlook on the direct detection implications for this. This is stuff that some work that just recently started with Neil Weiner at NYU. So direct detection now, we're shifting gears. This is a a different way to learn about the dark matter particle. Essentially, you're trying to detect the recoil from dark matter particles scattering off of nuclei in the centers, in some large tank that presumably is shielded to avoid backgrounds of radioactivity and from cosmic rays and so on. So there's lots of different detectors, as I mentioned in my introduction. There's semiconductor detectors and sodium iodine scintillation and so on. Lots of different people are trying to push this. So this depends on the local dark matter density and also on the distribution of velocities. And both of these, I think, our simulations can sort of at least shed some light on it or point out that there's uncertainties compared to the standard assumption, which what people normally assume is just like a density of 0.3 GeV per cubic centimeter and a velocity dispersion that is Maxwellian with a centered at 220 kilometers per second or so, and an escape speed of 500 or 600 kilometers a second. And I want to point out that while this, in our simulations, this quantity actually does not vary terribly much. As I pointed out before, there aren't very many subhalos locally, so you don't get a huge variance in the density. But the assumption of the Maxwellian is absolutely not the case. And this is particularly important for this whole gamma controversy, where they have reported this annual modulation, which arises from the fact that the Earth is moving around the Sun, and the Sun is flying through this dark matter wind produced by the dark matter particles in the galactic halo. And so this annual modulation that they detected depends on the velocity distribution of the dark matter particles. So the controversy here for gamma was that the dark matter particle that fits their modulation is ruled out by lots of other dark matter direct detection experiments for the sort of standard dark matter particle that people have generally considered. So that's what's shown here, the gamma preferred region in mass versus cross-section are these points here. This is from a paper by Savage et al. And the exclusion limits here from xenon 10 and from CDMS show that these regions are ruled out. This is true for a sort of standard dark matter particle. Then people have recently considered dark matter particle models, again, similar to the one I proposed, that I mentioned before by Akani Hamed et al., in which you have a slight extension to this. So this is inelastic dark matter. And so there, you're scattering, the dark matter particle itself has an excited state, so that's different from the standard dark matter particle. And only inelastic scattering is permitted. So you only get scattering off of the nucleus if you can actually excite this dark matter particle. So that means you need to have a high enough kinetic energy in order for this to happen. So this means that all of a sudden now you're more sensitive to the high velocity tail of the dark matter particles. So first of all, it also makes it easier to scatter off heavier targets because then your center of mass kinetic energy will be higher. So that favors gamma over CDMS, because gamma has iodine, which is a higher nuclear mass than CDMS, which uses germanium. It also increases the annual modulation because you are out on the high velocity tail. And the recoil spectrum is altered also, so you don't get any very few low energy events. So again, this favors gamma over experiments like xenon. But so just to wrap this up, in our simulations, we find that the distribution of velocities is not Maxwellian at all. So here I've picked all the particles at a radius of about 8.5 kiloparsecs. The dotted line is the best fit Maxwellian, and you can see that the distribution here departs from that significantly, especially at the high velocities. This has also been found by Mark Vogelsberger in the Aquarius group, and they showed also that this is robust to different halos. So they've simulated about 5 different halos, so they find that these kind of features are there. And so I'm running out of time here, so I'll just briefly show that this actually turns into a wide range of a large effect on the modulation. So this was plotted here. The amplitude is a function of the minimum velocity of the dark matter particle. And so you can see you can get amplitudes that are much higher than you would get with just the Maxwellian distribution. Here are the exclusion plots that you get out of this. So for best fit Maxwellian here, so the colorful lines here now are again the gamma preferred results, and these solid lines are exclusion limits from other particles. So here in this case, the gamma result is marginally excluded, but if you actually put in the velocity distribution from our simulations, you can see that this preferred region actually is no longer excluded, and well, yeah, here's a local variation of that too, where there's even an even larger departure from that. So the point to take away from this is that don't assume that distribution is Maxwellian, and if you depart from the Maxwellian and actually use something like that comes out of a simulation, then you can have particle physics models that allow gamma and CDMS and xenon 10 at the same time. Okay, so
But the phase of the oscillation phenomena, coincides with the time when the Earth is moving with the sun.
Yeah, right.
So then, like, that would indicate that these velocities are actually not so important, right? Newtonian should be okay.
that's what's shown here. So the peak day, as a function of the min, for the red line is for all particles within 8 to 9 kiloparsecs, and it actually is not strongly affected until you get to the very highest kinetic energies. And then what I'm showing here in these colorful, these green and light green and dark green are sort of local variations where I've just picked spheres at 8 kiloparsecs. And there you can actually get variations, you shift by 2 weeks or so. But yeah, so that is definitely a constraint that has to be factored in also. Okay, so I'll just put up my summary and say as I've tried to show you, the galactic dark matter halo is anything but smooth. It's very lumpy on all scales that we see. If it were possible to get some kind of indirect detection of this, that would test the very central prediction of CDM, namely all this small-scale structure. I've tried to show you that Fermi could possibly detect a handful of subhalos for these reasonable values of the dark matter particle physics parameters. And intriguingly, the leptonic signal may have already been observed by the Pamela signal and by through the ADIC signal. This needs more work, but at least it is still a possibility, especially when you consider dark matter models that exhibit the Sommerfeld enhancement. And then in the last few slides, I had to brush through them a little bit, but global departures from the Maxwellian can definitely affect nuclear scattering rates and can make some dark matter models consistent with DAMA and other observational experiments. Thank you.
Thank you very much for the talk. Are there any questions?
I have a question from cyberspace.
Oh, yes.
Jeremy Balin asks, I'm wondering about how the boost factor depends on 2 factors. 1, the observer's radius, and 2, halo and subhalo triaxiality.
Okay, so it does depend quite a lot on the observer's radius, the distance from the galactic center. I would say, as I tried to show you earlier, at the location of the Earth at 8 kiloparsecs, you find a very small boost factor. The halo is fairly smooth, and even when we extrapolate, we tend to get very small boosts. Now, for the halo as a whole, though, if you imagine the Milky Way halo, you put it out with the observers far away from it, and it's actually, in fact, an unresolved source, then you can get a very large enhancement from all the substructure that is in the outer regions of the halo. And that you have to again extrapolate, but you can get boosts of tens, hundreds. But again, then you also have to ask, what about individual halos in the Milky Way, for example, the subhalos that host dwarf galaxies or so? Again, there the boost is not likely to be super important because in the center, where all the dominant signal is, you don't get very much boost. In the outer regions where there is signal, but it's below, it has a very low signal to noise, that's where all the boost is, but it probably won't affect the overall detection significance very much. So really the boost factor is most important for external objects, and in particular for calculations of this sort of cosmological gamma ray background, annihilations throughout the history of the universe. I think that's where the boost factor is probably going to be most important. And then the other question was...
halo and subhalo.
Oh, the triaxiality.
He says this is done self-consistently in your simulation, but how would it be different if people assume spherical halos or something?
Yeah, but I'm not sure. I don't think it's going to depend very much on the shape of the subhalos. I mean, all the annihilation happens really in the very central regions, and I don't foresee triaxiality to change that very dramatically.
Well, for the bias that the disk lies on one of the axes, so it's not a random spherical position you should pick, but one where the disk is likely to lie.
Mm-hmm. Yeah, that's possible. But we don't even know how triaxial the halo is. In fact, lots of measurements seem to argue that it is very spherical. So.
Other questions? I have one question. What is your guess when we know what dark matter is?
Yeah, I don't know. I would not be surprised if we know what dark matter is in the next, certainly within our lifetime, in the next 10 to 15 years maybe, based on these sort of many different experiments that are coming online at the moment. I'm optimistic. I'm hopeful. I don't want to bet my year's salary on it or anything.
Okay. Thanks. So,
Thank you.
do that again.